Maybe I'll... Okay, so welcome everyone to the International Seminar on Automorphic Forms. Today, our speaker is Zhang from the Massachusetts Institute of Technology, and he will talk about Harris Venkatesh plus Stark. Robin.
Great, thanks. Thanks for the invitation. Very happy to be here today. And yes, I'll be talking about Harris Venkatesh Stark. So this we have three different components. So first, I'll talk about the two conjectures, the title separately, independently. That's our conjecture and the Harris-Venkatesh conjecture. I'm going to talk about the plus. So second part is on the unification of these two conjectures into one. So a unit conjecture and then finally, I'll go over one case in which this combined conjecture is proved. I'll introduce this later, but this needs to be called the imaginary angel case, and I'll just do an overview of the strategy and the ingredients that go into this of the imaginary dihedral case. Okay, so these are the three parts. Start and introduce the principal object study for us. So that's going to be F, a form of wave one. And let's say the level n. Okay, so weight one modular form F, we can associate by the work of the linea Serre, a Galois representation. So let me call this rho F, rotation of the Galois group of Q. And it's a two-dimensional complex representation. So, but in fact, I can take, instead of Q over Q, I can actually take a finite extension. So I can take a finite extension E over Q. And then two-dimensional representation rho F, I can actually associate another representation, the adjoint representation, rho F, and the three-dimensional representation. So okay, same group, but this is now three-dimensional complex representation, and you obtain this by the action through rho F on two matrices that are trace-free by conjugation. So say this is an action on by two free matrices. So these are the pairs. And the even looks like this. Take if you have some Galois groups, you can conjugate on through the matrix get through rho F. And in particular, the adjoint representation allows us to classify the modular form F because the representation factors through PGL, PGL2C, or if you like, this is a 3, and it has a finite image. So in particular, right? It's classically known that there are only 5 of subgroups of GL2C. So we have 5 possibilities. Either we have a cyclic subgroup, we have a dihedral.
Sorry, Robin, sorry to interrupt you. We can hear you, but there is sometimes the sound is breaking off a little. Do you think, is there something that you think you can do? If not, I think it will be okay because we can understand you. But
I can switch to the video from my iPad. Let me try that. How is this?
let's try.
Is this better or?
Maybe. I was thinking maybe it was the internet connection. I'm not sure what it is. Let's try like this.
Okay. Yeah, it might be my internet connection. Okay. Okay, so there are, right, so the adjoint representation factors through PGL2, and it has finite image, and so this could be either a cyclic subgroup, it could be a dihedral subgroup, or there are 3 possible exceptional cases, which would be A4, S4, and A5. So this is a 5. In which case, so these correspond to the case where F is called Eisenstein. F is a dihedral, or in the last 3 cases, we call F an exotic form. Right, so we can describe, we can classify our weight 1 modular form F based on the image of its adjoint representation. Okay, and also we have an integral structure on ad rho F given by elements of the following form. So we can take the integral structure of elements of the form 2 rho F evaluated at sigma for some Galois group element sigma minus the trace of rho F sigma times the 2x2 identity matrix. This is over sigma in the Galois group. Right, and you can take the z-span of these things, and this gives you a lattice in ad rho F. And in particular, we have distinguished elements. So for any place W, right, let's say this is of E. We have distinguished elements in ad rho F of that form, where we take sigma to be the Frobenius at W. So 2 rho F at the Frobenius of W minus the trace of rho F at the Frobenius of W times identity matrix. And this is a distinguished element of ad rho F. And note that, okay, so if W is an Archimedean place, what I mean by Frobenius of W is the complex conjugation. And okay, so for any place W, we get these special elements XW. This will come up in a second, but now let me draw a picture for the objects that I'm now going to introduce to talk about these conjectures. Okay, so from ad rho F, right, we have this Galois representation, and then we can study its arch and L function. So let's see, this is the arch and L function of ad rho F. And in particular, it vanishes at 0 with order 1. So we can look at the leading coefficient would be the first derivative of this Artinel function at 0. And what the star conjecture predicts is that there's a relationship between this derivative of the Artinel function and particular units in OE cross. Right. E being the number field that I had before from the Galois representation. Alternatively, instead of using this L value by the Rankin-Selberg method, we can also use the Peterson norm of F. This is the Peterson norm. They're proportional by a constant. So we can also take the composition of these arrows. This is still basically the star conjecture, just not as originally formulated. So let me just put a star here. But so this is a picture of the star conjecture. And so this is something happening over R, over C, a relationship between units in OA cross and the derivative of the Artinel function at 0 or the Peterson norm. Now the Harris-Venkatesh conjecture is like a mod P analog of this. So instead of units in OE cross, there's going to be some sort of mod P reduction procedure to get some reduction mod P of units in OE cross. So I'll explain this in a few minutes. And it relates this to, so now in the mod P setting, we don't have the Artin-L function or the Peterson norm. So we're going to need to find some mod P analog of this. So I'm going to have this FP cross norm, and this will be called the Harris-Venkatesh norm. Okay, and this is the subject of the Harris-Venkatesh conjecture. And I'm going to present them in such a way that there becomes sort of a natural unification of the two things. But yeah, so we have this real picture on the top, and then the bottom line is our mod P picture. And I'll talk about them in the following order. So maybe I'll start with the star conjecture and work from right to left. So we have the units, and then the star conjecture. And very briefly, I'll mention this Peterson norm. It's not actually going to play a very major role here in our talk, but I'll talk about that briefly and then move to the mod P setting. So we'll have the reduction mod P of units in OE cross, and then this replacement for the L function, or replacement for the Peterson norm. Okay, so this is going to be the picture that guides the rest of the first two parts of the talk. So let's start with the units. So instead of working directly with the units in OE cross, I'll work with a dual unit space. Just it'll make things a bit easier when I move to the mod P setting. So I'm going to define this dual unit space. I'll denote with a curly U. Add row F. So this is just going to be the space of homomorphisms from add row F, or really the integral structure that I gave on it, right? This lattice that I gave of these elements 2 row of sigma minus trace of sigma to OE cross. Okay, so this is what I mean by dual unit space, which is homomorphisms into this into the normal space of units. And on this dual unit space, then we have something called the Stark regulator. So this is the Stark regulator map is a generalization of the classical regulator map, and it sends this dual unit space to R. So I want some map reg R that sends this dual unit space to the real numbers. How is this defined? So if we pick Fix some Archimedean place. That's a fix an Archimedean place W of E. Right, then we can define this distinguished element that we had before. And this, so we have something in add row F. Then we can look at the evaluation map. So evaluation at our distinguished element. This sends something. So this sends our dual unit space to OE cross, right? And then we can compose this with the classical logarithm, and that'll give us something valued in R. So let's compose this with usual log, and this gives us a real number. Okay, so we have it in any Archimedean place W. We can take evaluation at this distinguished element, compose with logarithm. This gives us an R-valued map from the dual unit space. And in fact, this regulator map is independent of W. So you pick a place W to define it, but actually the map is going to be independent of W. And then, so now I can talk about the Stark conjecture, which relates, right, this L value to something coming from this dual unit space. And it follows a progression of a classical story starting with Chebyshev. So just to give some background on where the Stark conjecture comes from, Chebyshev in 1850 studied the leading coefficient of the Riemann zeta function. So let's say as S goes to 0, the Riemann zeta function looks like -1/2 plus some higher order terms. Okay, and then after you study the Riemann zeta function, maybe you want to look at Dedekind zeta functions, the next generalization of this. So that's given by the class number formula. So the work of Gauss, Landau, Siegel, all these classical people studied the Dedekind zeta function. I mean, usually it's phrased in terms of as S goes to 1, but we can take the functional equation to give it in this way. So the Dedekind zeta function as S goes to 0 looks like, so the negative class number of the number field times the classical regulator divided by the number of roots of unity. And then we have an order of vanishing given by the number of complex embeddings and real embeddings, -1, and then plus higher order terms. Okay, so we have the Riemann zeta function, and we have the Dedekind zeta function, the leading coefficient of the Taylor series expansion at S equals 0. And the Dedekind zeta function, right, decomposes into a product of Arts and L functions. So then the subject of the Stark conjecture is basically the same thing, but for Arts and L functions. So this was formulated in a series of papers by Harold Stark, 1971, 1975, 1976, and 1980. So the conjecture in general is more general than what I'm going to state, because it applies to any Arts and L function. But in our particular case, where we have this adjoint representation, it looks like this. So the Arts and L function is the leading coefficient is predicted to be coming from the Stark regulator of some unit, which I'll call Stark unit. And in this case, the order vanishing is just 1. and then we have some higher order terms. So actually, I need a verb here. So let me move this down. It predicts that there exists a unique Stark unit, a unique element of this dual unit space. Maybe tensor cube. So there exists some unique element of the dual unit space that gives the leading coefficient of this Artinel function. In general, the Artinel function could have order vanishing, larger order of vanishing, or could also have order vanishing 0. In general, it might not come from some particular unique element of this dual unit space, so there's more general formulation. But in this particular case of this adjoint representation coming from a weight 1 form, it's order vanishing is 1, and the leading coefficient should really come from some unique element of this dual unit space. And okay, so this might look a little bit different than what if you look at Stark's paper, if you look at Tate's formulation of the Stark conjecture, right? It'll look actually slightly different. Instead of, but this is actually equivalent. So classically, I'll just write it in case it looks more familiar. This is the same as the classical formulation where you have some denominator and a sum over the Galois group. And then the character of this representation evaluated as sigma with the absolute value, the logarithm of the absolute value of some actual unit in OE cross conjugated by sigma. So this is for some natural number n and some epsilon in OE cross. But it turns out that if you evaluate this dual unit at that xw, you get the same thing. Okay, so we have the classical Stark conjecture, and then I promised that I would mention the Peterson norm briefly. So let me just sort of make this remark. So the Peterson norm is a real number that we can associate to our weight 1 form F. And this is just a Rankin-Selberg convolution of F with itself. So say F, right, convoluted with its dual form, dx dy over y squared over x naught of n. This is some real number, and in fact, it's proportional to the Artin-L function that we care about, the L value that we care about. But we need, there's some constant proportionality, which I'll denote maybe constant, like some Rankin-Selberg constant, and they're proportional. So for the purposes of this talk, I'll use the two objects interchangeably because they're just proportional. So in the Stark conjecture, you can sort of replace this left-hand side by something by this Peterson norm, and then I just have to scale the unit, the Stark unit, appropriately. Okay, but now we can move to the mod P setting. So we have the top of the diagram that I drew. Mod P. So now we want to have everything valued in FP cross. So instead of the Stark regulator, we want some analog, so some sort of FP cross regulator map. And this is going to be defined very similarly. So I'm going to work with the same dual unit space that we had before, this curly U add row F. But instead of fixing an Archimedean place W, now let's fix a non-Archimedean place. Let's say it's over some prime P, like a rational prime P. So we can do the same thing. Take evaluation at xw, right? And this gives us, again, a map from this dual unit space to OE cross. But in fact, it gives us a map to OE cross and the part fixed by the Frobenius of W. And then, okay, so I'm going to omit some details, but there's a reduction mod W process we can do. So we can take reduction mod the ideal of W to give us something in FP cross, because in fact the image of this evaluation map lies in ZP cross. So we can take a reduction mod W to get something in FP cross. So I'm going to call this the composition of these things. Oops. My FP cross regulator map. It's a map that sends curly U add row F to FP cross. And so I also have to note, I'm cheating a little bit here also, because so anywhere in this talk where I write FP cross, I'm actually going to need, in reality, to tensor this with the field of definition of the Fourier coefficients of my modular form F. So, or the ring in which over which they're defined. So often I'll have to do something like this. Adjoin the, I mean here, yeah. If your modular form F, the Fourier coefficients lie in some ring of integers, I can write in this way: Z adjoin the values of the character of this Artin representation. But I'm gonna have to do this everywhere where I write FP cross. So in general, I'm going to omit this tensor product. So if your F has, say, integer coefficients, then it's actually an FP cross, and you don't have to write this tensor product. Okay, so we have this FP cross regulator map from doing almost the same thing, but just with a non-Archimedean place. So that's the right-hand side. And then the more complicated bit is for this left-hand side. So, right, so we need something, instead of the Artinel function, we need something on the left-hand side of this diagram. And this is given by something that Harris and Venkatesh call the Shimura class. So let me define the Shimura class. So that there's actually two constructions. There's one that's originally given in the paper of Harris Venkatesh. There's an alternate construction, a more explicit alternate construction that was pointed out to me by Loic Morel. Maybe I'll mention this very briefly, but I'll give the more geometric construction that was given by Harris and Venkatesh here. So we're going to work with some prime P not dividing. So P, we don't want P to be 2, and we don't want it to divide the level of our modular form F. Actually, for the first half of what I'm about to do, this condition won't matter, but it will matter later. Then we have an étale covering of modular curves. So you have x1 of P lying over x0 of P. And the deck group of this covering is FP cross. Right. Okay, so I mean, this covering is not actually étale. There's étale away from elliptic points. And I'm going to say FP cross, but actually in reality, we have to take out 12th roots of unity. So there's some problems at 2 and 3, but we have this covering. And from this covering, we can get something which I'll call the Shimura class. This is an element of H1 étale for curve x0 P, FP cross. Okay, so we have something in the first cohomology group. And now I'm just going to write a series of equivalences. So we can also write this as H1 étale of x0 P Z mod P minus 1 Z, tensor it with FP cross. And we can also rewrite this using the base change of the modular curve. This is also H1 et al. Of X naught P, tensor spec of Z mod P minus 1 Z, GA, again, tensor FP cross. But in fact, here, this Zariski, or this et al. Cohomology group is actually the same as the Zariski cohomology group. So I'm going to rewrite it again. The first Zariski cohomology group of this base change of this modular curve with O, again, tensor FP cross. And then by Serre duality, argument, this is the same as Hom of the weight 2 cusp forms to FP cross. Okay, so from this et al. Covering, what we get is this element of the first cohomology group, which we can actually interpret as a map from weight 2 forms, gamma naught P, to FP cross. Okay, so we have an FP cross value map acting on weight 2 modular forms, weight 2 cusp forms, that comes just from this covering of modular curves. And okay, so we have something acting on weight 2 modular forms, but right, we're starting out with the weight 1 modular form. So how do we make this act on that weight 1 modular form? So this is how we construct the Harris-Venkatesh norm. So with our weight 1 form, we want to construct a weight 2 form. And we're moving from, we start in level n, and we want something of level p. So what we do is we take f of z, and then we take its dual form, f star. So this is the modular form where if you take the Fourier expansion, all the Fourier coefficients are complex conjugates of the ones of f. So you take that and you evaluate it at pz, you multiply them together, and then what we get is weight 2 form that has simultaneously a gamma 1n structure, but also a gamma naught. Sorry, move this over. We have something that simultaneously has gamma 1n and gamma naught p structure. So we can take the trace of this to gamma naught p, and we have a weight 2 form of gamma naught p that we can then take the Schmorr class and act on it by the Schmorr class. And then we get something in FP cross, or this FP cross tensor, whatever, from F. That's a Harris-Venkatesh norm. So we get some value in FP cross by taking the Schmorr class and taking our weight 1 form and constructing this weight 2 form. Okay, so now we have 2 FP cross value things. We have this Harris-Venkatesh norm, and we have this FP cross regulator on units. So the Harris-Venkatesh conjecture gives a relationship between these 2 things. It's a conjecture of Harris-Venkatesh. The paper that formulates this was eventually published in 2019. So it asks that there is some natural number m and some units. So let me call it u. Oops. Let me make this the same color so I've been using. And some element u, the dual unit space. So note this u is not necessarily unique in this conjecture, such that this Harris-Venkatesh norm
given by the action of the Shimura class is equal to this FP cross regulator of U, and this is up to this integer m. And this should happen for all p not dividing 6n. So we have this integer m and this global object u, this element of the dual unit space, so that if you reduce it mod p for almost all p, we have this relationship mod p between Harris-Venkatesh norm and FP cross regulator. And yeah, so
can I ask?
Yeah.
What does M depend on?
Here M just depends on F, and U depends on F, but they're not necessarily unique.
But they not on P.
Not on P. They don't depend on P. Yeah. So you have these two same objects, so that when you reduce, like, it simultaneously satisfies this mod P for almost all P.
I see. Okay. And another question: is the Harris-Venkatesh norm computable in practice? Like from the Fourier, like what does one have to do to compute it? Right.
So this is a good question, and this is part of the remark that I wanted to say earlier. So there's an alternate construction of this Shimura class thing. So let me just say, so there's a forthcoming work by Loïc Morel and let me flip them around, by Emmanuel Couturier and Loïc Morel. And they give a more explicit formula for the left-hand side, so for this Harris-Venkatesh norm. So maybe call this in progress. And this uses like the work of Borisov Gunnels and uses modular symbols, but they have so this is not, this is not on archive yet or anything, but they give an explicit formula for the left-hand side of this. And this comes from an alternate construction of the Shimura class, which I can outline briefly here. So let me see, alternate construction of Shimura class. It goes like this. So if you have, so you can take, say, weight 2 modular forms, not cusp forms, of gamma 1p. And there's a surjective map from here onto modular forms of weight 2 of gamma naught p, right? This is a trace map. And inside the space of modular forms of weight 2, we have the cusp forms of weight 2. Okay, so you can also look at how this trace map behaves down here, but it's not surjective at this bottom level, right? So if you take the trace map of like the pre-image of the trace map for cusp forms, it might not come from another cusp form on gamma 1p, but it might come from, it'll come from some modular form for gamma 1p. So let's say we have some G here. And in fact, we can take G to be this form that I constructed before from F. So we have some weight 2 cusp form. Look at its pre-image under the trace map. So say its pre-image is G prime. So this is the trace pre-image G. Then the way they define the Shimura class acting on G is in the following way. We take a product over every element FP cross. Okay, and really we have to, again, mod by 12th roots of unity. You take T raised to the constant Fourier coefficients of A0 of T times that pre-image, so G prime. Right, so we have an action on this space by FP cross, or really mod mu 12. But then we get this element of FP cross defined by taking a product of everything and looking at the Fourier coefficient of the pre-image under this trace map. And you can show that this is equivalent to, like, this is equal to the Shimura class action from this covering of modular curves. So there's like explicit expression here, and actually they give an even more explicit formula in terms of data from F in an upcoming work.
Thank you.
Yeah. Okay, so this is the Harris-Venkatesh conjecture, and okay, I should also sorry, I have 15 more minutes. Is that right?
Yeah, maybe you can go a little over time because you started like maybe, I don't know, 18, 19 minutes.
Okay. So okay, let me move on to the second part, the unified conjecture. Okay, so in the way I presented them, the Stark conjecture and the Harris-Venkatesh conjecture here look quite similar. So let's make them more similar. This is put them in one framework. So this is going to be called Harris-Venkatesh plus Stark. Okay, so now I'm going to ask, like in the Stark conjecture, that there's some unique element of the dual space. We call it UF. And maybe let me tensor by Q, because I don't want to impose some integrality that's not in the original Stark conjecture, such that one, the Stark conjecture holds. So the Peterson norm of F is equal to the Stark regulator of this element. Or if you prefer, you can replace the Peterson norm by the constant multiple of the derivative of the RTL function. And I also want the Harris-Venkatesh conjecture to hold. So the FP cross regulator, and have this be equal to the Harris-Venkatesh norm of the same unit. And here now I'm going to say for all sufficiently large P. Right, so okay, so the second part looks slightly different than the Harris-Venkatesh conjecture that I just stated. But actually it's the same thing, it's equivalent. So each part is equivalent to Stark and Harris-Venkatesh, respectively. The way that you see the second one being the same as Harris-Venkatesh is that, so if we look at this equality here and you multiply both sides by some m, that causes this equality to vanish for small p. Like if m is divisible by p minus 1 for some small p, then we make both sides vanish. You can get a m on the left side, and then remember the unit is not unique in this original formulation of Harris-Venkatesh, so we can scale our UF to become some other U. So asking that this thing holds without an M for sufficiently large P is actually the same as saying that there is some M for almost all P, for P that are not 2, 3, or dividing the level of N. But furthermore, so not only is this, these two conjectures independently, but also this imposes an additional compatibility on the Harris-Venkatesh conjecture. Because now we're really fixing the unit. We're saying that this has to be true for the same unit that came from the Stark conjecture. Right, and let me say maybe, so what is known about this? So the main theorem of the talk, let's say, is that Harris Venkatesh plus Stark is true for all imaginary dihedral F. So I need to say what that means. So recall, for dihedral forms, a form being dihedral means that the image of the adjoint representation, right, in PGL2C is isomorphic to some dihedral group. And in particular, when this happens, we get the special property that the original Deligne-Serre representation, rho F, is actually the induced representation of a character. So this induced representation of a character of the absolute Galois group of some quadratic number field. Chi here is a non-trivial finite character of the absolute Galois group of K bar over K, where K is a quadratic number field. And so we naturally then have two cases where either K could be imaginary or it could be real, right? So when I say for all imaginary dihedral F, what I mean is, so for all the weight one modular forms that in the dihedral case where K is actually imaginary, so where the Deligne-Serre representation comes from a character that comes from an imaginary quadratic number field. And this follows, so this is following some previous work. So first is that I don't need to prove the Stark conjecture, because Stark, in his 1980 paper, already proved the Stark conjecture in this case. So the last paper where he formulated the Stark conjecture proves it for imaginary quadratic number fields. So that part is already known. Stark conjecture is true. Let me just say the imaginary dihedral case. Stark conjecture is true in this case. And then a work of Darmon, Harris, Roche, Venkatesh, 2022. They show that the Harris-Venkatesh conjecture for imaginary dihedral forms is true if two assumptions hold. So the first assumption they make is that the discriminant of this imaginary quadratic number field, dk, is an odd prime. So they assume the discriminant is an odd prime. So this condition is not so hard to remove, and is not so serious. The more serious condition that they impose is that chi is an unramified character. So chi is unramified everywhere. Right. So one of the difficulties, so they use the classical language of modular forms, and in the classical language, it proves to be very difficult to generalize their arguments to treat ramified characters. So one of the things that we need to do is we in my thesis, I italicize their entire argument and then make some modifications to be able to treat some ramification. But let me also remark that there was another work that tried to treat these ramified cases, and this was by Emmanuel Le Couturier in 2023. So he works on, like a slightly weaker form of Harris-Venkatesh. What I mean is that, so I move over here to Harris-Venkatesh, over here. So for one, instead of working in FP cross, he projects FP cross to Z mod LZ for L that divides P minus 1, but whose square does not divide P minus 1. Okay, so it's a partial picture of FP cross. And second, he has an ambiguity of sign. So there could be a sign, say a -1 on one of the sides that depends on P. So there's some ambiguity of sign for every single P. So this is what I mean by like a weak Harris-Venkatesh. But what's interesting is that, so he shows that a weak Harris-Venkatesh is true for some ramified cases. So he has some assumptions, but they differ from the assumptions of Darmo-Harris-Venkatesh. But what's interesting is that this uses a slightly different approach. So there's a theta correspondence argument in Darmo-Harris-Venkatesh that he bypasses using the special L value formulas of Waltz-Piaget and Ichino. So the triple products, essential L value formula, these formulas. And then you can see maybe this is how the sign ambiguity comes up, right? Because there's some squaring, like for example in Waltz-Piaget's formula. But so our approach follows the one of Darmo-Harris-Venkatesh. Let me first explain their general strategy, and then how one can move on from there to prove the general conjecture. So Darmo-Harris-Venkatesh, right? We have some imaginary quadratic number field here, K over Q. And furthermore, they assume that it has odd prime discriminant. So let me maybe change. Yeah, okay, let me just write the dk is an odd prime. And we have this character chi, the character of absolute Galois group of K, which they assume is unramified. And then there's one important observation that they make, which is that the Harris-Venkatesh conjecture is, so originally what I used to say is that it's trivial if P splits in K. So assume that we can assume that P is inert. But here I'm using maybe the English language poorly. So Harris-Venkatesh is trivial in the sense that both sides are trivial. So we have like 1 = 1. But then Akshay pointed out to me when I gave this talk that it was highly non-trivial to observe that you get 1 = 1. So it's non-trivial to observe that it's trivial. So I should not use the word trivial here. Let's say it's like 1 = 1. It's not a trivial observation to show that there's nothing happening on both sides. Okay, so in the case when P is inert, they have this chain of equalities, which now I'll write out. The Harris-Venkatesh norm, right? Let me just recall the definition. The Shimura class acting on this weight 2 form we've constructed from F. And let me just write this as a pairing. So I'm not doing anything mathematical yet. Okay. And they show that the pairing of this weight 2 form with the Shimura class is equal to the pairing of the Shimura class with another weight 2 form, which is going to be the theta lift, a particular theta lift, which maybe I don't have so much time to actually talk about, but there's a theta lift coming from the trivial character tensored with xi, where xi is, let me just write it here. Xi is the antinorm of chi. So it's chi divided by chi composed with complex conjugation. Okay, so with these two characters, you view them as automorphic forms on some quaternion algebra, and you get some theta lift. But this gives us some other weight 2 form, and they show that it's the same as the pairing of the Shimura class on the original weight 2 form. And then they look at the dual theta lift. Dual theta lift. And they show that this is something called a higher Eisenstein element. Let me explain this in a second, but this is basically, you can think of it as like a generalized eigenfunction. It's eliminated by higher powers of higher powers of the Eisenstein ideal rather than by the Eisenstein ideal. And they get an explicit description of this in such a way that they can construct some Stark unit, or in this case, an elliptic unit that gives us the FP cross regulator. Okay, so let me maybe write what some of these ingredients were. So everything gets moved to some definite quaternion algebra B. Which we can write as B equals K plus Kj of discriminant P. And so square bracket is a map from Hecke characters to automorphic forms on B. And we have a theta lift, which takes automorphic forms on 2 copies of B, and sends that to weight 2 cusp forms. And then we have this epsilon P, which was a higher Eisenstein element. So something eliminated by powers of the Eisenstein ideal. Okay, and then, okay, so let me say, so what happens if we remove the assumption that the discriminant is an odd prime and that chi is unramified? So in this chain of equalities, actually, the second half of the argument works. So the construction of the unit and the part with higher Eisenstein element, this still works if chi is a ramified character. But where the argument breaks down is here. So showing that the Shimura class acting on our original weight 2 form is the same as, gives the same value as the Shimura class acting on this theta lift. This argument done in the classical language doesn't work if chi is ramified. So what do we do? So one of the key ideas is to introduce something called an optimal form. So the name of this comes from optimal orders. This is going to be a 2-variable modular form. So 2 arguments, Z1 and Z2. This is a 2-variable modular form. So right, this is something on like 2 copies of modular curves. Or if you prefer, its automorphic realization is something that lies in the automorphic cuspal representation generated by F tensored with the automorphic cuspal representation of its dual form, or the contragradient. So this is explicitly constructed, and it's uniquely determined by the following fact. This is an explicitly constructed two-variable modular form that actually, if you evaluate it at z and pz, this literally gives you the theta lifting that they use. For all p not dividing 6n. Okay, so we have a two-variable modular form that literally gives this theta lifting. So we have an equality here, f opt z comma pz. I mean, since it's equal to the theta lifting, of course, its pairing will also equal the theta lifting. And then, right, we need to relate these two things. And this is done, this top to bottom step is done by a like a modular representation theory argument. So let's say there's a multiplicity one argument, mod, say mod, I don't know, mod L to the T. So it's a positive characteristic multiplicity one that allows me to compare the pairing on this optimal form with the original pairing. So in fact, this equality holds for anything. So I can replace this with anything that's in this representation pi f, tensor pi f star. So any sort of test vector in this tensor product of representations, actually we can compare mod L, we can compare, or mod P with the original pairing. So that's the key idea, to go from top to bottom. Everything else only needs maybe some minor modifications. So this is how sort of you can prove the entire Harris-Venkatesh in full generality for imaginary dihedral forms. And let me remark that also this construction also works. It should also work in the real dihedral case. So they have a similar, like a different chain of equalities in the real dihedral case. But this should also work in that case. So this should also be able to treat the real dihedral case. So that's a work in progress. And this optimal form is constructed explicitly. So from theta series, where you have characteristic functions of optimal orders, and it's done in such an explicit way that we can actually can compute m in the original conjecture, or p naught, where you need p sufficiently large, means that it holds for all p bigger than some prime p naught. We can actually compute and describe explicitly how large p has to be to satisfy the Harris-Venkatesh conjecture. Finally, this construction also works for many exotic cases. So optimal form construction optimal forms can be constructed for many exotic cases, and I should note the exotic cases. You believe that the conjecture should be true because there's actually been numerical data, or like experimental evidence, in a paper of David Marcil in 2021. There's numerical evidence for the conjecture holding, and we can construct optimal forms and sort of do this, up to here. But of course, the problem in the exotic case is that the star conjectures are not known. In the cases that we need the star conjecture, there's been no general progress on these cases since Stark formulated his conjectures in 1980. So without being able to construct a unit that even holds for the star conjecture, we would also need the same unit to give an equality between these things in the exotic case. So So in some sense, the difficulty of proving this in the exotic cases now is the same difficulty as proving the star conjecture. But yeah, won't take any more time. But yeah, thank you. Thanks for listening.
Thank you very much. Thanks, Robin.